Alright, welcome to another dose of torture. I'm I'm your usual dead person. Let's get started. So, data is generally distributed, and we'd like to see where it's distributed. We'd like to see where most data points would lie. And so these distributions will have two statistics, or they'll have two parameters if you're looking at the whole population. It will have a measure of central tendency, which is mean, mode, or range. That's wrong. That's really okay. I fixed it. Nobody saw that. It's so central tendency is either mean, mode, or median, and then measure of variation is range or standard deviation. And normal distribution is the main distribution, right? It's basically it's the big boss of them. So here's what normal distribution looks like. It's symmetrical, it's nice, it's very curvy, and the key thing is it'll have the mean, the median, and the mode all at the same point at the very middle. Okay? Now you'll notice that there's a bunch of numbers down here. We'll talk about those in a bit. The key thing to focus on is that the mean, mode, and median are all in the middle, and it's symmetrical. So you don't always get that in real life. You can have skewed distributions. Okay? So if you have a positively skewed distribution, the mean will be bigger than the median, such as in graph B over here. Okay? So as you can see here, it has a tail that points to the right, which basically means that there are some big values on the positive end that are pulling the mean to the positive side. So it's skewing the mean towards the positive. Basically, all this means is it's no longer symmetrical, the mean, median, mode aren't in the same place, it's not normal anymore. The key thing is that the mean is bigger than the median, so it's positively skewed, and the tail is to the right. Or the tail could be to the left, which would basically mean that the mean is smaller than the median because it's being pulled towards the negative. And so it will have its tail towards the left. We call this negatively skewed. Okay? And finally, if you look at this graph down here, you'll see that distributions can also have more than one mode. So for example, if we look at the average height of the population as a whole, you'll notice that we have two modes. And that's because you'll have one where most of the male heights are, and another one where most of the female heights are. Okay? So, let's look at each of those two statistics that we talked about up here, central tendency and variation. Let's look at them into more detail. So, central tendency. This is what biostatisticians will care about a lot because it's where most of the data probably is. Okay? And so we usually find this by looking at the mean, the median, or the mode. The mean, that's the numerical calculated average. The mode is the most common value that you found. And the median is the central value. So, you're already prepared for this. We're going to do an example. Let's just get into it. So, let's say you're part of the Russian Kremlin, right? And you're trying to influence US politics to get some weird orange-looking fellow to become the president. So, you'll generally try to use targeted memes to help promote their propaganda. But you might want to check how well those memes are doing. So you'll look at the views for the posts that you've made on 3 different websites. You're going to look at Twitter, you're going to look at Red Dot, and you're going to look at YouTube but pronounced in Korean. So on Twitter, you found this data set. On Reddit, you found these number of views. And on YouTube, you found these number of views. Okay, so let's take Twitter as an example, right? Like I said, to find the mean, like I've said before, to find the mean, all you have to do is add them all up and divide it by the number of data points that you have. So here we have 1, 2, 3, 4, 5, 6. So you add all of these up and divide it by 6. Okay? To find the mode, all you have to do is look for the most common data point, which in this case it's just 1700, right? You can see it here visually because there aren't that many. There's two of them here. It's the most common one, and so it's the mode. Now to find the median, this one's a little bit more complicated, so I'm going to pull out the pen. But like I explained in the last video, you order them from highest to lowest. Now I already knew that I was going to do this, so I already did it. So I already ordered them for you. And what you'll do is you'll count, okay, so there's 6 of them here. 6 divided by 2, that's 3. So 6 divided by 2 equals 3. Ignore this, let's pretend I can actually write using a mouse, okay? And we can both live in peace. Okay, so because this is an even data set, you can't just round up or down. What you're actually going to do is, where is my mouse? Is you're going to count 1, 2, 3. So you're going to take this one and 4. You're going to take both of these and you're going to find the average between them, which will come out at around 1,477. And so what they did is they found the mean, median, and mode for these 3 data sets. Now I did some off-camera work, I did some off-camera grinding, and I already did it for you. So Twitter, we had the mean being this much, the median here being 1477, and the mode being 1700. Now for Reddit, the mean was 3800, the median was 3700, but there was no mode, because if you noticed, all of these values only happen once. None of them are repeated. Okay? And for YouTube, we had the mean being 4500, the median being 4000, and the mode was 3045. Right? That's because, as you can see here, 3000 happened 3 times, and so it's the most common value, it's the mode. Okay? And so you'll notice here that the mean, the median, and the mode aren't the same. Okay? Now, generally, because in real life, you probably won't get them to be the same, but if they're generally pretty close, we can consider it to be normal or close to normal. But in this case, this data is pretty skewed. Okay? Now, in the case of skewed data, you don't really want to use the mean, because, like we said before, the mean is affected by outliers. The mean can be affected by extreme data. So in this case, you might want to prefer to use the median for this specific data set. Okay, how do you find the median? So we order the set in ascending order, and we find the middle value. Okay, so if you missed the last session, if it's odd, then you just take the data set. In this case, we have example data set. Let me just so we have our data set, we ordered it from lowest to highest, and then we started knocking them, and then we counted them. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 divided by 2 is 6.5. Okay? 6.5, it's because 13 is an odd number, then we don't have to find any averages. You just take 6.5 and then you round it up to 7. And so you go 1, 2, 3, 4, 5, 6, 7. This is your median is 4. Okay? So example 2, we have this data set. Actually, all I did is I just removed the 9 from the previous data set. We ordered them from lowest to highest, okay? And so for this one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay? So this is an even one. So again, you're going to divide it by 2, okay? So you're going to do 1, 2, 3, 4, 5, 6, okay? And you're going to take 6, the 6th one and the 7th one. Again, it's very important that you order this from lowest to highest. Okay, I've made the mistake before where I forget to order them and it does cost you marks. Alright, so you take the 6th value and the 7th value and you find the average. So in this case, it's 3 plus 4 divided by 2, that's 3.5. Pretty straightforward stuff. So the mean, this is the most fancy one, but really all you do is you ignore all of this fancy notation stuff that's happening here at the beginning. You just add them all up, and then you divide by the number of participants. All right, so in this case we had 8 participants, and we took their ages. This is the data set. We just add them all up and divide by 8 because there's 8 participants, okay? And so you get 23.25. All right, pretty simple. So statistical models, all right? Probability models, they're not exact, they aren't perfect, but what you can do is you can see how good they are at predicting what will happen in the real life situation. All right, so what you'll do is you'll develop the model, you'll predict something, and then you'll compare it to what actually happens. All right, so let's take an example. You know, I'm pretty sure you've gotten used to it. We're going to do a lot of examples here. So the odds of developing cancer is influenced by many factors, such as age, gender, lifestyle, family history, and so on. So let's make a nice simple equation. So cancer equals age plus gender plus lifestyle plus family history plus genetics plus E. So what is E? Now in this model, E is the error of the model, and so it's basically all of the factors that could cause cancer that aren't any of these other factors that we made over here. So they're not any, so it's not age, so it's not any of these factors over here, but it's all of the other factors that could lead to cancer, right? So in this case, it could be smoking, alcohol, diet, whether or not the patient exercises, what temperature room they sleep at, and stuff like that, right? There's a lot of stuff that can cause cancer, so, there's a lot of stuff that can influence cancer. And so, you know, there's a lot of stuff that will fall into this E. Okay? So, we can rewrite this as variables because this equation has a lot of words in it, and it's very long. So, Y here is the dependent variable, or how likely you are to get cancer. And X is your independent variables. So the X's, X1, X2, X3. These are your independent variables, right? Such as age, gender, lifestyle, genetics, and so on. All right? And E, that is your error of your model. That is the error level of your model. Okay? So what exactly is E? Okay, I've said that it's the error. I've said that, you know, it's the stuff that you didn't measure, the stuff that isn't included. Basically, it's all of the variables that could have been included in the model, in theory, but you didn't actually include them when you made the model, right? So it's all of the variables that you didn't measure and the variables that you can't measure. And you didn't measure them maybe because it's too costly, maybe because it's too unethical, maybe it's purely random, or maybe it's like too complicated and you don't really want to do it. Okay, so let's take our cancer example and look at a couple of things, a couple of variables, you know, that could fall under E. So one example is telomere length. Sorry for the PTSD from genetics, but you know, it's unrealistic to take every single patient, pull out their DNA, and go, okay, so the telomere is exactly 3 micrometers long. Okay, so this patient's pretty likely to get cancer. Oh no, this one's 5 micrometers. Okay, they're good, they're safe. That's pretty unrealistic to do in practice because you can't just pull out all of the DNA from a patient. That would be pretty expensive, and I don't think they'd like it. So another variable that's very difficult to control is replication errors. The reason is that these are completely random. So in a patient, you can't really control them, and it wouldn't really be ethical to, you know, force mutations inside a patient. All right, and the third variable that you can't really control, because you know it's far too unethical to expose doctors to toxic materials, is whether or not the patients play League of Legends. So here's a couple of things to remember about the mean. Now, the mean is affected by outliers, unlike the median. But what this does mean is that you can expand the sample size, you can use big sample sizes to stabilize the mean. And again, you can't use the mean on nominal or ordinal data. Now, this line over here is a little bit wacky, it's a little bit complicated, but basically what it's saying is that if you were to calculate the mean from a binary data, then what it would give is it'd give the proportions, okay? So here's the example that we're going to look at. Here's our data set. we decided to look at the genders of these 10 participants that I decided to torture for my entertainment. And so we gave each gender a value, a 0 for female, 1 for male, because, clearly the doctors that made this example were sexist. But hey, don't kill me for being the messenger. Again, we're going to use the fancy equation. And so it'll give you, and so if you add up all of these zeros and ones and divide it by 10, because there's 10 patients, it'll give you 0.2. So 0.2 times 100, that's 20%. So 20% of your participants were male. Okay? Pretty straightforward stuff. All right, so the second statistic that we talked about all the way up here is measure of variation. All right? Now, we have a couple of ways to measure variation or variability. The first one we could look at is range, which is where you take the biggest value and the smallest value and you find the difference between them. Okay, so basically biggest minus smallest. And then there's standard deviation, which is a bit of a fancy schmancy calculation, but we will look at it in a bit. Okay, so there's a bunch of others, which are these ones down here. There's coefficient of variation, I have no idea what that is anymore. Percentiles, which we did look a little bit at in the previous video, where we saw the 25th and the 75th percentile. We're going to look at this in more detail later on, so don't worry too much about it. And there's the interquartile range, which we already talked about before, so I'm not going to go over it again. So here's the range. It's pretty simple. You just take the biggest value and the smallest value, and you find the difference between them. Again, this is affected by outliers. Okay, so that means it's very cringe generally. So let's look at this example. We had 8 participants that don't have a life, and we measured their age. All right, and here are their ages. And so we decided to find the range, so that's just the biggest value minus the smallest value. 38 minus 17, that's 21. Okay, but let's say, hypothetically, that we added an extreme value. So let's do it again, but this time we tossed a curveball. Instead of 38, your doctor accidentally, because they don't have any handwriting at all, instead of 38, they wrote 388. Okay? So you did the calculation again. 388 minus 17 is 371, which I don't know if you guys have noticed this before, but 371 is pretty different from 21. They're not exactly the same value. All right? And so because range is affected so heavily by outliers, let's look at a better method, which is standard deviation. So standard deviation allows you to find the average distance of the data points that you have from the mean. Okay? So the distance from the mean is represented by this equation over here. So basically it's data point minus the mean. All right? And so you find the average distance, which is you do data point minus mean for all of your patients, and then you divide it by the number of patients. Let's just do the example that you all know is already coming. So we took these 10 patients that I decided to torture for everyone's entertainment, and we took their age. Okay? And so we took their age and we found the mean of the age, which is, by the way, this fancy, x. We call it x bar. So it's because it's x with a bar on top. And so we took their ages, we found the mean of the age, which is adding them up, divided by 10, that's 37.1. Okay? So then what we did is we found the difference between each of the patient's ages and the mean age, which pretty much what we did is we went 32 minus 37.1, that's negative 5.1. Okay, negative 5.1. 45 minus 37.1, that's 7.9. Okay, 7.9. 29. 29 minus 37.1, that's negative 8.1. All right, next patient, 40 minus 37.1, that's 2.9, and we did it for all 10. Now, if you do this, and then you find that the mean of these 10 distances, what you're going to get is 0. And if you actually did your calculation correctly, you will always get 0 no matter what data set you have. Okay? And generally, zeros aren't very useful. If your mean is a 0, then it's probably not that useful of a mean. Okay, so what do we do to fix it? Well, there are two methods we can do. We can use absolute values, or we can square the differences, which basically means is we take minus 5.1 and we square it, because if you square a negative, it will always turn positive, because negative times negative is always positive. Or you can do absolute values. Now, I personally think absolute values is just a whole lot easier, because if you just look at it, oh, okay, because what absolute values does is it just goes, okay, negative 5.1, all right, ignore the negative, it's just 5.1. Negative 8.1, all right, just ignore the negative, it's 8.1. Negative 7.1, all right, just ignore the negative, it's 7.1. That's what absolute values does. I don't know why they don't use it. In the PowerPoint, it said it's more complicated, but let's be honest, that's just cap. We all know it's cap. So let's be honest, nobody knows why they don't use it. Okay, I don't know why they don't use it. But what they do instead is they square it, which is more annoying, but that's what we're going to do because that's what you're going to do in the exam. And so here's what it looks like after we square it. Now you'll notice that instead of finding the mean by dividing the sum of differences, or the sum of squared differences, by the number of participants, we divided it by the number of participants minus 1. Now we call this n minus 1 degrees of freedom. Okay, so what exactly is degrees of freedom? Well, let's take this quick example. So we have 5 values here, 7, 4, 6, 5, 8, and we found their mean, which is 6. Okay, so let's say we wanted to change the values without changing the mean. Well, we can take the 7 and make it 3, all right? We can take this 4 and we can make it 6. We can take this 6 and we can make it 2. We can change 5 to 7, if you want. But what happens to the 8 is to make the mean stay at 6, the 8 will have to change on its own. All right? We can't control what the 5th value is, what the last value is. All right? So that is what degrees of freedom is. It's how many values can you change without changing the mean. And for any experiment that you do, it's just the number of patients minus 1. Okay? Because you always need to leave 1 that will correct any changes that you make. Okay? So here's your example for standard deviation. So we had the same 10 patients from earlier that I decided to torture. And so again, the mean age for them is 37.1. And here are the distances. Okay? And so what we did is we found the square of each of these differences. So we took minus 5.1 squared. That's 26.01. And we did this again for all of these 10 participants. And here is the differences squared. Okay? And then we added all of these up to get 574.9. And so that's this value up here. So 574.9 minus n minus 1, which is degrees of freedom. So n, which is the number of participants, that's 10. So your degrees of freedom is 9. So 574 divided by 9, that's 63.88. Okay, so this is your variance, which is 63.88. Now, because in this example we measured their age in years, the variance, which is s squared, will be measured in years squared. But this unit isn't very helpful, right? Like years squared isn't a very helpful age unit. So what we'll do is we'll square root this, we'll square root the variance, which will convert years squared into years. So the standard deviation, which is the square root of the variance, is 63.88 square rooted, which will give you 7.99. So this is the standard deviation, which is the main tool that they use to look at variability, especially when you have normal distribution. And standard deviation of a population, which is represented by sigma, this Greek letter over here, And again, because it's of a population, then that makes it a parameter. And so you can estimate parameters using samples, using statistics. And so you look at the standard deviation of the sample, which is represented by the symbol SD. Okay? And if you have a bigger SD, then that means your sample was more varied. Okay, so you just had more different patients. And so we use standard deviation more than the variance because, again, it has the same unit as the mean. So if you look back at this example, like we said, the variance was measured in years squared, which isn't a very useful unit. Whereas the standard deviation is just measured in years, which is much more useful. Okay, so here's a quick recap. We had distributions, which have two statistics or parameters, depending on whether you're looking at samples or populations. They'll have a measure of central tendency, which is your mean, your mode, or your median, and I made the same mistake twice. There we go. Now we can all pretend that I don't make mistakes ever. And we have your measure of variation. And we have your measure of variation, which could be range or standard deviation. Okay, so this is where we're going to add on, and we're going to bring back the normal distribution. So in a normal distribution, okay, you'll have a constant amount of data points within one standard deviation, and you'll have another. You'll also have a constant amount of data points within two standard deviations, and a constant amount of data points between three standard deviations. All right, and so generally speaking, you'll have 68% of patients, for example. 68% of them within one standard deviation of the mean. You'll have 95% of them within two standard deviations of the mean, and you'll have 99% of them within three standard deviations of the mean, which, is almost all of them. So on a graph, here's the normal distribution graph, this green area, this represents one standard deviation. So between the mean and one standard deviation, we'll have 68% of patients. So this green area is 68% of patients. And then between the mean and two standard deviations, which is the green area and the yellow areas, that's 95% of patients. Okay? And then between the mean and three standard deviations, that's almost all of the patients at 99.7%. Sorry if this was a little complicated and, a little intense. If it was confusing, just let me know, and I don't know, I might re-record it again, try and make it simpler. But hey, I guess go take a rest, go eat something. Peace.